We continue NCERT miscellaneous exercise of chapter 5. The question is, if x minus a the whole square plus y minus b the whole square equals to c square, c is the constant, then prove that 1 plus dy by dx the whole square whole raised to the power 3 by 2 upon d2y by dx square is a constant quantity. So we will find dy by dx first and then d2y by dx square. So differentiate with respect to x, 2x minus a, and drop a square. Differentiation of x is 1 and differentiation of a is 0. Plus this becomes 2 into y minus b, and differentiation of y is dy by dx equals to differentiation of c square is 0. So 2 times of y minus b and dy by dx equals to minus 2 times of x minus a. 2 and 2 gets cancelled and we get dy by dx equals to minus x minus a upon y minus b. So we get the value of dy by dx. Now it will be differentiated again, d2y by dx square, d2y by dx square. So this will be differentiated on the form u by v. So x minus a, v as it is, y minus b as it is, and d by dx of u minus u as it is, and d by dx of v and upon v square means y minus b the whole square. Now put the value of dy by firstly we will differentiate. So d2y by dx square equals to minus y minus b, and differentiation of x is 1 and differentiation of a is 0, minus x minus a. Differentiation of y is dy by dx and differentiation of b is 0, and upon y minus b the whole square. Now we put the value of dy by dx. So d2y by dx square equals to minus y minus b, and the value of dy by dx is minus of x minus a upon y minus b. Already there is minus, so minus minus becomes plus. X minus a into x minus a, it gives x minus a the whole square and upon y minus b. We have substituted the value of dy by dx upon y minus b the whole square. So by taking LCM we get y minus b the whole square plus x minus a the whole square upon, this goes at denominator place and it becomes y minus b the whole cube. And at the place of this, at the place of numerator, x minus a the whole square plus y minus b the whole square, we can write c square. So minus c square upon y minus b the whole cube. This is the value of d2y by dx square minus c square upon y minus b the whole cube. Now we put the value of dy by dx and d2y by dx square in this expression. So 1 plus dy by dx the whole square. The value of dy by dx is this. When we make it whole square, minus becomes plus and it gives x minus a the whole square upon y minus b the whole square. So this is 1 plus dy by dx the whole square and whole raised to the power 3 by 2 upon d2y by dx square. The value of d2y by dx square is minus c square upon y minus b the whole cube. Solve this by taking LCM. We get y minus b the whole square plus x minus a the whole square upon y minus b the whole square, and this is whole raised to the power 3 by 2 upon minus c square upon y minus b the whole cube. Now x minus a the whole square plus y minus b the whole square, again this is written as c square. So we get c square raised to the power 3 by 2 upon y minus b the square whole raised to the power 3 by 2. 2 and 2 gets cancelled and it comes y minus b the whole cube, and this will be written in the multiple form. So it comes to be into y minus b the whole cube upon minus c square. So this and this gets cancelled, square and 2 cancelled, and it becomes c cube upon minus c square, which gives minus c, which is a constant value. So this proves the result that the value of this is a constant quantity and minus c is a constant quantity. Now we discuss question number 19. Question number 19. Prove by mathematical induction. Prove by mathematical induction. Prove by mathematical induction that for all positive integers, that for all positive integers, prove by mathematical induction that for all positive integers, d by dx of x raised to the power n is equals to n into x raised to the power n minus 1. So we have given d by dx of x raised to the power n equals to n into x raised to the power n minus 1. So we will prove that this expression is true for n equals to 1. For n equals to 1, the value of LHS will be calculated. So d by dx of x raised to the power 1, and we know differentiation of x is 1. And for n equals to 1, the value of RHS 1 into x raised to the power 1 minus 1 means x raised to the power 0, and x raised to the power 0 is 1. So we can write, since LHS is equals to RHS, so this is true for n equals to 1. This expression is true for n equals to 1. Now we will suppose, let it is true for n equals to k. This expression is true. We will suppose that this expression is true for n equals to k. So d by dx of x raised to the power k, at the place of n we will put a, and on the right side also k into x raised to the power k minus 1. Name it first equation. Now we will prove that this statement is true for n equals to k plus 1. we will prove that. Let this is true for n equals to k plus 1. So put the value of n equals to k plus 1. So d by dx of x raised to the power k plus 1 equals to k plus 1 x raised to the power k plus 1 minus 1. So we get d by dx of x raised to the power k plus 1 equals to k plus 1 and 1 cancelled, x raised to the power k. Now we will prove that LHS equals to RHS. So LHS d by dx of x raised to the power k plus 1 is written as x raised to the power k into x. So d by dx of x raised to the power k into x. We will differentiate on the form u into v. So u as it is means x raised to the power k as it is, and d by dx of x plus v as it is and d by dx of x raised to the power k. So x raised to the power k and differentiation of x is 1, x as it is, and from equation first we will put d by dx of x की power k is k into x raised to the power k minus 1. This is written as x की power k plus x into k into x raised to the power k upon x. X and x cancelled, and for both the terms x raised to the power k is common. So we get k plus 1 into x raised to the power k, and which is equals to RHS. Since it is true for n equals to k plus 1, since it is true for n equals to k plus 1, therefore it is also true for n equals to k and for all positive integers. We have proved that this expression, this statement is true for n equals to k plus 1, and if it is true for n equals to k plus 1, then we can say that it must be true for n equals to k and also for all positive integers. Now we discuss question number 20. Question number 20. Using the formula sin A plus B. Using the formula sin A plus B equals to sin A into cos B plus cos A into sin B. Find the formula, derive the formula for A plus, derive the formula of, derive the formula for cos of A plus B using differentiation. Using differentiation. We have given sin A plus B equals to sin A into cos B plus cos A into sin B, and we have to derive the formula for A cos A plus B using this formula. So we write the formula sin A plus B equals to sin A into cos B plus cos A into sin B. Now differentiate both sides. With respect to t. Differentiate both sides with respect to t. So d by dt of sin A plus equals to d by dt of sin A into cos B plus d by dt of cos A into sin A. Now differentiation of sin theta is cos theta. So we get cos A plus B. Now drop sin and differentiation of A with respect to t is dA by dt and differentiation of B with respect to t is dB by dt. Use the formula u into b. So sin A as it is and d by dt of cos B plus cos B as it is and d by dt of sin A plus this will be differentiated again on the form u into b. So cos A as it is and d by dt of sin B and plus sin B as it is and d by dt of cos A. So cos A plus B and dA by dt plus dB by dt equals to sin A. Differentiation of cos B is minus of sin B and drop cos. Differentiation of B is dB by dt plus cos B as it is. Differentiation of sin A is cos A. Drop sin. Differentiation of A is dA by dt plus cos A. Differentiation of sin B is cos B. Then drop sin. Differentiation of B is dB by dt plus sin B as it is. Differentiation of cos A is minus sin A and differentiation of A is dA by dt. So we take dA by dt as form. So we have two terms containing dA by dt. So we can write cos A into cos B and minus sin A into sin B and common dA by dt. Then we take dB by dt as common and we write cos A into cos B and minus sin A into sin B and dB by dt. From both the terms, we take common as cos A into cos B. Cos A into cos B minus sin A into sin B will be taken common from both the terms. Then we get dA by dt plus dB by dt. And on the left side we have cos of A plus B and dA by dt plus dB by dt. So dA by dt plus dB by dt gets cancelled from both the sides and we get the formula for cos A plus B equals to cos A into cos B and minus sin A into sin B. So this is the formula for cos A plus B using differential coefficients of sin difference using the formula for sin A plus B. Next we discuss question number 22. If y equals to determinant fx, gx, hx and LMN, A, B and C. Fx where y equals to given, then prove that dy by dx, then prove that dy by dx equals to f dash x, g dash x, h dash x, L, M, N and A, B. This we have to prove. So differentiate, and the differentiation of determinant is, firstly the first row will be differentiated and rest of the rows will be written as it is. In the next step, second row will be differentiated and first and third rows will be written as it is. In third step, the third row is differentiated and first and second row will be written as it is. So differentiation of y is dy by dx. Now we differentiate the first row. So differentiation of fx is f dash x. Differentiation of fx is f dash x. Differentiation of gx is g dash x, and differentiation of hx is h dash x, and L, M, N as it is, A, B, C as it is. In first step, we have to differentiate first row, second and third row would be written as it is. In the second step, first and third row would be written as it is. So fx, gx and hx, and second row will be differentiated. L, M, N are constant term, their differentiation will be 0, and third row will be written as it is, plus first and second row would be written as it is. So fx, gx, hx as it is. Second row would also be written as it is, and differentiate third row. A, B, C, they are the constant quantities, so their differentiation will be 0. Now we know the property of determinant. In determinant, if any row or any column is 0, then its complete value will become 0. So we will write f dash x, g dash x, h dash x, and L, M, N, A, B, C, and this expression becomes 0 because second row is completely 0, so whole expression becomes 0, and this will be also becomes 0. So we get the result dy by dx is equals to f dash x, g dash x, h dash x, L, M, N and A, B, C. So this complete the result. Next question number 23. If y equals to e raised to the power a cos inverse x, e raised to the power a cos inverse x. Then prove that y equals to e raised to the power a cos inverse x. Then prove that 1 minus x square d2y by dx square. 1 minus x square d2y by dx square minus x dy by dx minus x dy by dx and minus a square y equals to 0. This we have to prove, and we have given y equals to e raised to the power a cos inverse x. So differentiate both sides with respect to x. Differentiation of y is dy by dx. Differentiation, this will be differentiated d by dx of e raised to the power a cos inverse x. Then we drop e and d by dx of a cos inverse x. So differentiation of e raised to the power x. It gives e raised to the power x. A is the constant term taken outside. Differentiation of cos inverse x is minus 1 by root 1 minus x square. So do cross multiplication. Under root of 1 minus x square dy by dx equals to minus a into e raised to the power a cos inverse x, and the value of e raised to the power a cos inverse x is written as y. So we will write 1 minus x square and dy by dx equals to minus a into y. At the place of e raised to the power a cos inverse x, we can write y. Differentiate again. Differentiate again with respect to x. So root over 1 minus x square as it is, and differentiation of dy by dx is d2y by dx square plus differentiation of root 1 minus x square. So 1 by 2 root 1 minus x square, drop the square root, then it comes 1 minus x square, differentiation of 1 is 0, and differentiation of minus x square is minus 2x, and dy by dx written as it is equals to minus a, and differentiation of y is dy by dx. So 2 and 2 cancelled, and it gives root over 1 minus x square d2y by dx square plus minus minus, and x by root 1 minus x square dy by dx equals to minus a and dy by x. By taking LCM, root 1 minus x square is LCM. We get 1 minus x square d2y by dx square minus x dy by dx and minus a root 1 minus x square and dy by dx. We have taken LCM and then we have done cross multiplication. Now 1 minus x square and d2y by dx square minus x dy by dx equals to minus a, and at the place of under root 1 minus x square dy by dx, under root 1 minus x square dy by dx, we can write minus of ay. So minus a into minus of ay. and the result we get 1 minus x square d2y by dx square minus x dy by dx equals to minus minus plus a square y. A square y will come on left side. So it gives 1 minus x square d2y by dx square minus x dy by dx and minus a square y equals to 0. So this thing we have to prove. 1 minus x square d2y by dx square minus x dy by dx minus a square y equals to 0. So this complete chapter 5th. From next video we will discuss new chapter, application of derivatives, chapter number 6.